Okay, so good morning, everyone. As I was saying, my name is Mustafa. I'm a PhD student here at UNH doing theoretical physics and quantum gravity, especially. I will be your Physics 401 instructor for this class this summer, along with Chetra. We will be your physics instructors. So what we have on the agenda for today, the outline is first, we will discuss some logistics, office hours, and course structure. Office hours are already, I don't want to take much time talking about that. I will just send you a poll after class so we can see what times you are available at. Then we will introduce physics. What is physics and why do we study physics? And we will go on to discuss some physical quantities and units, unit conversions, and metric system, English system, and stuff like that. Then the first formal study of physics, like the actual beginning of the course, starting from displacement, vectors, and scalars, those are in chapter 2, kinematics, basically. I will be working from the textbook. I sent you the textbook on the syllabus. If you click on the name of that, let me actually show you. This is the syllabus. If you actually click on the name of the book, it goes right away to the book, and you can get a PDF version of that as well. Let me go back to where I was. Okay. So each time I explain something, I will refer you to the sections in the book discussing the same content as I will be. Okay. We will have lectures, and by the way, the lecture is recorded just in case if anyone missed a lecture. I'm not saying you should miss lectures, but just in case. In-class activities, these are usually just small problems that I will give you during lecture just to engage in the learning process and not be bored. These will be graded for participation only. So you will not be penalized for making mistakes. It's just for participation, and it accounts for 20% of your total grade. Lab activities, these are just experiments, since for this course, it's, physics is experimental science, so we need experiments. We will try our best to have an experiment for each topic. And usually we will aim for Wednesday to have experiments, but that's also depending on the pace of the course. It's a 5-week-long course, it's super fast. So we will try our best to cover all the material. Experiments will also be graded for participation. Then there are homework and quizzes / tests / exams, whatever you want to call them. Homework will be released on Monday morning each week. I will release it right after class, and will be due on Friday midnight. That might seem short, but the problem is when I first assigned it, I thought I would make it weekly, like released on Monday and then submitted on Monday, but then I wanted to have quizzes on Thursday. So you will not have feedback before the quiz. So that didn't make sense. So I switched them. So the homework will be due Friday midnight. So you can get the solutions to that homework and feedback during the weekend, so you can study for the quiz, which will usually be the following Monday morning before moving on to our next topic. Once the homework is released, of course, you will not be able to solve all of it at once because we will have not covered all the content. So for example, today we will cover displacement, vectors, and scalars, and physical quantities. So I already wrote the homework, but I haven't uploaded it yet. Let me make sure I'm sharing my screen to Maybe I'm sharing the correct screen. Here. Am I sharing the correct screen here? Yeah, okay. So by today's lecture, you should be able to solve problem 1 and problem 2 on the homework. Not problem 3 onwards. Those will be covered during next classes. Probably by tomorrow, you will be able to solve 3, 4, and 5. And then on Wednesday, you will be able to solve 6 and 7. And on Thursday, you will be able to solve 8. And then you will have the rest of Thursday and the whole of Friday to work on the homework collectively, just to review, or if you have any questions to ask me. And that's why I guess office hours make sense to be on Friday. So you can work on the homework and collect all questions you want. So we will discuss that later. But that's for homework. Quizzes will be usually an hour long on the first hour of one day. They will cover the topic that we covered the previous week. They will be a little, I will not say harder, but on the same level as homework, not easier. And they are worth 30% of your grade. The lowest homework grade and the lowest quiz grade will be dropped. So you don't need to worry too much about that. I think that summarizes our discussion about logistics. Oh, I forgot to mention an important thing. Since Chetra and I will be co-teaching the course together, each one of us will be covering a topic. So I will start doing kinematics, and then Chetra will do forces and dynamics, and then I will do momentum and so forth. So we will keep switching topics, but each one of us will teach a whole topic, not lecture and lecture notes, a whole topic. And in-class activities and lab activities are done in groups. So when we grade them, we only take one person at random and grade their work and give the rest of the group the collective grade. Of course, it's for participation, so there is not an actual grade, but just the feedback. But homework and quizzes are done or are submitted individually. You can work on them. You can work on homework in groups, not quizzes. You can work on homework in groups. You are actually encouraged to do so, but you must submit your own work at the end. Okay? That summarizes our discussion of logistics. So let's start. So this is logistics. Let's move on to the next item, which is introduction. Those are sections 1.1 and 1.2 in the book. This is just a warm-up. Okay, so what is physics? This is a summary of what physics is. It's a branch of science that studies nature and how the universe behaves. But like, we all know that the world is very complex, right? In its details. And each of us observes a great variety of phenomena and objects every day. So we are curious creatures, humans. So we want to understand. We want to see what's going on and be able to explain it. So over centuries and centuries, we have collected questions, we have collected information, and we have cataloged all of this information. And we didn't expect them to be connected to each other. We have just collected information. But surprisingly, a surprisingly small number of laws and theories explain all of this information. And it seems that despite the complexity that appears on the surface, nature at a fundamental level exhibits order and simplicity. And this is what makes science in general possible, and physics in particular possible. because physics is the simplest of sciences. It's not the easiest, it's the simplest, because it concerns itself with the basic elements of nature: matter, energy, space and time, and their interactions. That's it. That's all physics is concerned about. As you increase in complexity, you go, for example, to chemistry, and then you go to biology and so forth. So you increase the complexity of your systems. So physics, of course, follows the scientific method. Of course, you guys all know the scientific method, but just for a refresher, you start by an observation, and then you try to make a hypothesis to explain that observation. Then you test this hypothesis experimentally, see if it passes the test. If it fails the test, then you refine the hypothesis again and test it. If it passes the test, then you keep testing. You never stop testing your hypothesis. If your hypothesis passes a lot of tests, then it becomes a theory until someone falsifies it. Okay, so any claim science makes has to be falsifiable. And physics, of course, follows that. And that's why we have experiments and we have labs. So why do we, this is just the summary of what I said. It's a branch of science that studies nature and how the universe behaves. And it covers everything from the tiny charged particles in the atom to motion of people, cars, galaxies, galaxy clusters, like the whole universe, okay? Why do we study it? As I said in the beginning, we're humans, so we're curious. That's one thing. But not everyone is interested at that fundamental level of understanding. You can just be practical and say, okay, I want to get something out of that. I don't want to dig that deep. So physics has a lot of applications, lots and lots of applications, literally everything around us, like computers, this projector, this, like literally anything. But since this course is more focused towards life science students, so I just got some applications from biology. It helps understanding cell walls and cell membranes. This is on the microscopic level. It helps understanding the heat, work, and power of the human body. And this is on the macroscopic level. And if you think about X-rays, MRI in the diagnostics, and cancer radiotherapy, et cetera, et cetera, et cetera. Okay, so it has lots and lots of applications. Okay, this summarizes the motivation of why we do physics. Now we will move on to the next topic, which is physical quantities and units. As I said in the beginning, physics is an experimental science, so it follows the scientific method. And the scientific method has experiment in it as a crucial element, right? So to be able to experiment with the concepts we develop, we have to have numbers. We have to have quantities to talk about. We have to be precise about the quantities we talk about, right? So we define the physical quantities as the qualities of the system that can be reasonably and reliably quantified. Okay, so actually let me write that down. Physical quantities are defined as the qualities of the system that can be reasonably and reliably quantified. And as examples, you have, for example, mass, you have length, you can have temperature, you can have speed, etc. All of these are physical quantities, and you can see that some quantities are more fundamental than others. For example, mass, length, and temperature are more fundamental than speed, because speed is length over time. So it's like derived from more fundamental quantities. So physical quantities can be defined in two ways. Physical quantities. You can either define them by how they are measured, and this is usually for the fundamental units like mass, length, and time. You cannot define length except by saying the length of the object is that when you compare when you compare it to the length of another object, you just say how you measure it. And time, for example, you define time as change. You define it as like the movement of the sun, as we see it in the sky, the periodic motion of the pendulum. So it has to be something periodic and changes. So you only can define it as the measurement of how you measure it, okay? So this is, for example, as length. Or by stating how it's calculated from other measurements. And this is like speed is calculated as distance over time. And this is a description, like it's a way of telling you, okay, get the distance, get the time, measure them separately, and then divide them by each other to get the speed. So it's not a fundamental quantity, it's a derived quantity that we define it this way to assign it with physical quality of the object. So these are the two ways we can define physical quantities. Now, what's a measurement? If we look at this definition, how they are measured, okay, how do we measure something? What's a measurement? If you want to think, for example, about length, what's a measurement of length? What does it mean when I tell you, okay, this pen is 12 inches or something? What does that mean? Right, right. Exactly. But even before talking about standardized units, measurement is just a comparison, right? You compare two physical quantities of the same type. For example, the length of this pen. I can come up with this eraser and say, okay, I have 2.5 erasers in this pen, right? It's just a comparison of two physical quantities of the same type. So, but if I do that, even though this is a valid measurement, it's not meaningful. It is meaningful, but it's not helpful, right? If I tell you that, you don't know how long you don't know how long the eraser is. So that's why we come up with standardized units to communicate meaningful information among scientists, right? And that reminds me of a piece of news that I remember that I was searching about it before class. Actually, I already saved the yeah. this. So, so this is an example of a measurement that is valid, but it's not really like, please don't do that. Okay, don't type your answers in washing machines unit. Okay. Yeah, moving on. So let's define measurement. I'll just write what I said. It is a comparison of comparison between two physical quantities of the same type. And same thing, for example, if we're measuring mass or weight, you can say, okay, I weigh 3 times as much as this chair, but this is not helpful. So that's why we come up with kilograms or pounds or standardized units. Okay, so standardized units, standardized units are agreed upon units used to meaningfully communicate information. Yeah, okay. Okay, for standard units, we have 2 famous systems. First system is the SI system of units, also known as metric system. And the English system of units, also known as the imperial system of units. SI system is the system that uses meters, kilograms, and seconds. That's for length, mass, time. All systems use seconds for time, but anyway. And English system uses feet or inches, pounds, and seconds. So historically, the English system was used in nations once ruled by the British Empire. It is still used right now in the United States, but almost everywhere else in the world, the metric system is used. Okay. And in science, the metric system is used as well because it's easier and it's more systematic. For example, in the English system, you have the conversion between, I wrote them down somewhere. You have 1 mile is equal to 5,280 feet, where 1 foot is 12 inches. Okay. On the other hand, you have 1 kilometer is equal to 1,000 meter, and a meter is 100 centimeter, and so on. It's base 10. So by multiplying or dividing by tens, you move from centimeter to meter to millimeter to micrometer to nanometer to kilometer, just by using the same unit and adding the correct prefix. So we will be using the metric system in this class. And sometimes you will be given English units, but just to convert that or to understand how unit conversions work. So let me give you the prefixes and then give an example on that, on a conversion. So we have the prefixes. We have giga. We have mega. We have kilo. We have nothing. We have milli. We have micro. Actually, it goes here. And nano. And of course, you have Santi and DC and Deca, but those are just actually those here are the ones that we probably will use. We will probably just use kilo, milli, and small subset of them. But giga is 10 to the power 9 of the object. So if I say gigameter, it's 10 to the power 9 of a meter. No one uses that, but it exists. 10 to the 6th, it's mega. So if I say megawatt, for example, it's 10 to the power 6, which is a million of what? Kilo is 10 to the 3rd, which is 1,000. So when we say kilometer, this is 1,000 meter. When we don't say anything, this is just 1 or 10 to the 0. Milli is 10 to the -3 or 0.001. So millimeter is 0.001 meter. Micro is 10 to the -6. Nano is 10 to the -9. Micro is usually corresponding to microscopic dimensions, hence the name. And nanometer is usually on the atomic level. So for example, the radius or the diameter of an atom is about 0.1 nanometer. I don't know if that number is correct, but it's on that order of magnitude. Okay. So let's give an example of a conversion, and then I will give you guys a couple of examples to work them out. Let's say we want to convert 15 miles, and I want to know how many meters are in 15 miles. Okay. So what I know is 1 mile is equal to 5,280 feet. And 1 foot is equal to 0.3048. I just Googled these numbers, so don't memorize them. And that's all I know. Okay. So what I do is I multiply by conversion factors. So I say 15 miles is equal to 15 miles times 1, right? I didn't do anything. But instead of this one, I will remove it and write 5,280 feet over 1 mile, because this is just 1, right? Then the units cancel up and down, and this is the trick. That's why I put it this way. So this is now 15 times 5,280, which is, I calculated in the calculator, 79,200 feet. Okay, now I want to go from feet to meter. So again, I play the same trick. I multiply by a conversion factor that has feet in the denominator, so it cancels. So I put 1 feet here, and up I will have 0.3048 meter, because that's equivalent to 1 foot. Again, the units cancel, and I get 79,200, multiplying that, and the resulting number will be in meters. So that's 140 meters. Once I get the answer is meter, I can go to kilometer, I can go to centimeters, I can go to whatever units I want. So this is also equal to 24.14 kilometers, just divided by 8,000. Okay, so this is the trick. You just write down the conversion factors and place the units you want to cancel in opposite order. So if you want to cancel the unit in the numerator, you put the same unit in the denominator and have the equivalent unit you want to go to. Okay, so I will give you 3 questions on unit conversions. Let me write them down here. In class questions. So given a speed of 100 kilometer per hour, convert it to meter per second and mile per hour. Question 2. A large soccer field is 115 meter long and 85 meter wide. What are its dimensions? In feet and inches. Then the third question and the final question is, what is the height in meters of a person who is 6 feet 1 inch tall? Okay, I will give you the conversions. You have 1 mile equal 5,280 feet. What else? Okay, take 2 more minutes and then we will do it together and then you guys take a break. Then we will move on to the next topic. Okay, so let's start working out the first problem. So we want to convert, let's start with meters per second. Or actually, let's start with miles per hours because it has hours and that would be simpler. So we have 100 kilometers per hour, okay? And we want to convert that to miles per hour. So we want to convert kilometers to miles, but we don't know the direct conversion rate, conversion factor. What we know is each kilometer has 1,000 meters, and each meter is related to feet this way, and each feet is related to mile this way. So we will go backwards. So this is equal to 100 kilometer per hour times 1 kilometer in the denominator and 1,000 meters in the numerator. So the kilometers cancel. And I will be left with meter per hour. Then I also want to cancel the meters. So I will have meters in the denominator. 3048 meters. And those are equivalent to 1 foot. Okay. I need more space. So again, the unit will cancel meter with meter, and I will be left with foot per hour. And then from feet to miles through this relation up above. So that will be another conversion factor. I need feet in the denominator. So 5,280 feet equivalent to 1 mile. And once again, feet cancels. And the only unit I'm left with is miles per hours. And I multiply all the numbers together. So this is just 100. This is the original 100 that we have times 1,000 over 0.3048 times 5,280. So this is the big conversion rate that takes kilometer per hour to mile per hour, yes. And this answer will be miles per hour. And I calculated that earlier. It is 62.1 mile per hour. Okay. Is that what you guys got? Okay, great. Now we go to meter per second. Okay. we repeat the same process again. (100 km/h) is equal to 100 km/h times, and now I want to go to meter per second, so I will convert kilometers to meters and then hours to seconds. So this is multiplied by 1,000 meters over 1 kilometer. Kilometers cancel. And then I want to cancel the hours, so I will have an hour in the numerator to cancel with the one in the denominator, and that's equivalent to 60 minutes. Then minutes themselves, 1 minute is equivalent to 60 seconds. So now minutes cancel, hours cancel, and I'm left with 100 times 1,000, 60 times 60 meter per second, and that's 27.8 meter per second. Okay. We do the exact same thing for problem 2 and 3. It's just different units. So I will do problem 3 just for the sake of time, and I will skip problem 2. Okay. So let's do problem 3. We are given 6 feet 1 inch tall. So there are 2 ways to go about this. We can first convert this 1 inch to feet and then convert the feet to meters, or we can convert feet to meters, inches to meters, and add them together. So let's convert 1 inch to feet and then add it to the 6 feet we originally had, and then convert all of them. So the height is 6 feet plus 1 inch. So this is 6 feet plus the inch. I will multiply it by a conversion factor 12 inch in the denominator and 1 foot in the numerator. So the units cancel. So I have everything in feet now. So this is 6 plus 1 over 12. And this is 6.083 feet. And now this is standard to calculate, to convert it to meters. 6.083 feet. You would just multiply it by the conversion factor, 0.3048 meters, which is equivalent to 1 foot. Units cancel, and you get at the end 1.85 meters. Okay, so it's just a standard procedure. You insert conversion units, and each conversion unit is 1, basically, because you have something in the numerator and have something equivalent to the denominator, but in different units. And you choose to arrange your units in a way that cancel the unit that you don't want. Okay. So that's all about units. You guys have 10-minute break. And after that, we will start discussing kinematics, which is the actual beginning of this course. Okay. Do you have any question? Huh? How do you want to round? Yeah, actually, it doesn't matter so much in that class. So yeah, you can round it to two decimal places. Yeah. I skipped the whole discussion about accuracy and significant figures because it will take more time than we can afford. But yeah, you can round it to significant figures. So now we will move on to chapter 2, which is the actual start of the course. These are the actual questions that you will have on homework and exams and so forth. Except for one question on unit conversions on first homework. So let's start with chapter 2, kinematics. And to be specific, it's one-dimensional kinematics. Okay. First section of the chapter is displacement, talks about displacement. But actually before that, what is kinematics itself? Any thoughts? What is kinematics? So kinematics, interestingly, is of Greek origin. The word kinematics itself, it means motion, okay? And interestingly enough, the word cinema for movies is coming from this word as well. Kinematics is defined as the study of motion without referencing to its cause. So we don't care what caused that motion, but we just study the motion itself. So kinematics is the study of motion without considering its cause. Okay. Motion means the change of position over time, right? Everything around us in motion. You will not see anything static. Even in inanimate object like this table, you have atoms inside that move around and juggle around. So everything is in motion. And to be able to discuss motion, we need to have a way of discussing position with a quantified way, right? So we cannot just say the object is there or here. These are ambiguous words. So we need a mathematical device that will allow us to discuss position, okay? So position is where an object is at a particular moment of time. It is measured with reference to a fixed point. So if we're talking about this room, for example, this room would be called a reference frame, the technical word. And if I want to measure the position of this pen, I will say, for example, this pen is 8 meters from the wall. So the wall is fixed point in the reference frame. With reference to this point, I say my pen is this far, okay? And the reference point is arbitrary. So instead of saying it's this point from the wall, I can say it's this point from the whiteboard, or it's 2 centimeters from my computer. So the reference point is arbitrary, but it has to be specified for your statement to be meaningful, okay? So you have to have an origin of coordinates. We need to construct a coordinate system to have the full device. So coordinate system. So the procedure is as follows. You will choose an origin of coordinates. Choose an origin. And we will be discussing only one-dimensional motion, like motion on a line in this chapter. We will not concern ourselves with 2-dimensional or 3-dimensional motion because it's just a generalization of one-dimensional motion. It's easy to understand if you understood one-dimensional motion. So we will concern ourselves with one-dimensional motion, which Could be just you driving your car on a lane, right? You're just moving in one line. You stop, you accelerate, you decelerate, you move with constant velocity. This is motion in a line. So that's what we will be discussing. Okay. So choose an origin. This will be your fixed point. Okay. So let's say I pick a point here and say this is my origin. Then draw an imaginary axis along the motion of that, along the motion of the object in study. Imaginary axis along the motion of the object studied. Okay, so let's say we picked the origin to be here, and this line is the line of motion along which the particle or the object is moving. Your car is moving along that line, okay? The origin will be called the point 0. So we denote the position by x. X equals 0 will be the origin of coordinates, okay? And this axis describes the motion along the line. Now this axis is like a ruler, okay? You mark it at equal positions. So 1, 2, 3, 1, 2, 3, 4, and so on. So 1, 2, 3, -1, -2, -3, and so forth. With positive being on the right to the origin and negative being on the other side, which is the negative of the coordinates. Of course, you can switch that. This is arbitrary, but this is often the case that to the right is positive and to the left is negative. So this is number 3. The position is I mean, you locate the position by reading the ruler mark, right? So if I say, for example, I have a car here, I already defined my origin of coordinate to be here at x equals 0. So I can say a meaningful statement that the position of the car is 1. This is with reference to this coordinate system. It's that would mean the car is 1 meter to the right of this point. This point could be, for example, a traffic light. I specified the traffic light, and then the car is 1 meter to the right of the traffic light. If instead I said, okay, there is a tree here, then this position of the tree will be -3. And the interpretation of that statement is that it's 3 meters behind the traffic light. So positive and negative indicate directions, and position is just a number that tells you distance from the origin point. Okay. So number 4 in the procedure is that positive / negative indicate which side of the origin, which side of the origin. So all of that together is a coordinate system. That's what we mean by a coordinate system, okay? So you have a reference point, you have equally spaced marks, and you have an object. This object is located at some point, and this is how we describe it. And this is very important because based on that, we will define velocity, we will define speed, we will define acceleration, and we will define everything. But in every calculation, you have to specify your coordinate system. Otherwise, you will have negative signs everywhere and you will have incorrect results. So this was the coordinate system. So what is displacement? the title of the section. What's this displacement? Displacement is denoted delta x. Displacement delta x. The big delta, the Greek letter, indicates the change or difference. So delta x is defined as x final minus x naught or x initial, but I'm just using the convention of our book. So this is the final position, and we explained what position is above, and x naught is the initial position, right? So, for example, if I have again my my coordinate system with x being 0 here, the origin, and I have 1, 2, 3, -1, -2, -3. And let's say I started the motion, like I started my car here, okay? And then after some time, I'm here. So this is x naught, the initial position, and this is x final, okay? So I moved from here to here. The displacement in this case is 3 meters. All of these are in meters, just to be clear. Should be kilometers because it's a car, but anyway. 3 meter minus 0. So the displacement is 3 meter. Okay. What if I took the same graph, but instead started here as the initial position and ended up here? Will anything change? What do you think? It will be negative, right? Because the final position is now 0 minus 3 meter, which was the initial position, which is negative 3 meter. So the negative sign in this case indicates direction, right? So in one case, the motion was to the right, and in the other case, the motion was to the left. And that's what makes a quantity not just a scalar, but a vector, because a vector is a quantity that has both size and direction, right? So displacement is a vector, and in more than one dimension, it will be pointing at an angle and so forth, but we will just be focusing on one dimension. So it's either to the right or to the left. Okay. So this is displacement. How about this graph? Let me add one more. Again, 0, 1, 2, -1, -2. Let's say I will stop drawing a car. I will just put a point and say it's a car, okay? Let's say we started here, moved up to this point, and then went back to this point and stopped here. It's motion in one line, but I just moved it up a little bit to have a space. So I just moved forward and then stopped and moved backward again. So this is the final position and this is the initial position. Okay. What is the displacement in this case? What do you guys, what do you think? 2? Okay, it is 2, right? Because it's 1 minus 1. So it is 2 meters. Okay, so in this case, the displacement is this vector. Okay, pointing from -1 to 1. However, this is not the distance traveled. So if you were driving your car, you will have on your display, you will have more than 2 meters. You will actually have 4 meters. read on your display, because distance is, or distance traveled is the whole thing. Like you moved this much and then you moved again this much. Okay, so there is an important difference between displacement, distance traveled, and just distance. So let's define them carefully here. Displacement, distance, and distance traveled. Okay, displacement is as we defined it above. It's delta x equal final position minus initial position, and it's a vector quantity. So it has both magnitude or size and direction. Okay. It only depends on your initial and final position. It doesn't depend on the path traveled in between. So it doesn't depend on the path traveled. Only initial and final points. Distance, what we discussed now was distance traveled, not distance, but distance is just the magnitude of displacement. So it's the size of displacement. So it doesn't care whether the displacement was to the right or to the left. It's just 2 meters. Doesn't matter if it's positive or negative. You just take the absolute value of that because that's the distance. It doesn't make a difference if I move forward or backwards. It's just the same distance. Okay. So distance is, let's call distance, let's call it D. And it will be the absolute value of delta x in mathematical terms. Okay. So it is a scalar quantity, not a vector quantity. It's a scalar quantity. So it only has a magnitude. Magnitude only. Okay. It still doesn't depend on the path traveled because it's the magnitude of displacement, and displacement itself didn't depend on the path traveled. So in the above examples, we have here, for example, here, the distance traveled, the distance here was 3 meters, and here the distance as well is 3 meters. Even though the displacement is negative, distance is still the same because the amount of meters covered is the same. The distance traveled is the whole distance taken along the path. So it depends on the path you took. Let me take a look at the definition I wrote down here. It is the total length of the path traveled between two positions. It is the total length of the path taken between two positions. And this is, of course, different than displacement because displacement didn't depend on the path traveled, okay? Distance traveled depend on the path traveled. This is also a scalar quantity because it doesn't have direction. It only depends, it's only a number. We have examples of vector versus scalar quantities. For example, if you think about velocity, velocity is a vector quantity. If you think about driving your car this way, it's different than driving your car that way. It's different. We also have, we will see later on in the course, forces are vector quantities because you can push a chair this way and it's different than pushing the chair that way. The result is different. Scalar quantities are like temperature, for example. There is no direction for temperature. Temperature is just a number, right? Even if you have negative number for temperature, that doesn't mean direction in that case. It just means the reference point is different. When you say in Celsius, for example, the water freezes at 0 temperature. Below 0, you will just have ice. But that doesn't mean there is a direction, okay? So there are lots of examples of vectors versus scalars, but the important point is that a vector has both magnitude and direction, whereas a scalar doesn't have a direction. It's just a magnitude, okay? And these 3 quantities will help you answer the second question on the homework here. I will upload the homework right after class. So question 2 on the homework, it's exactly that. You're asked about distance traveled and magnitude of displacement, which is the distance, and displacement from start to finish for 4 different curves, which is exactly what we did here. And first question is just conversion methods. So by the end of this class, you'll be able to solve 1 and 2. Go back. Yes.
Travel now, or just doing along the x-axis, right?
Just along the x-axis, yeah. Just one-dimensional motion. And in the homework, it's also in the x-axis only. It's just drawn this way because there's no space. We will not be covering 2-dimensional and higher dimensional kinematics in this class, because I was told it's not relevant really for biology applications. I would have loved to do projectile motion and stuff like that, but it's not really relevant. So we will concern ourselves only with 1 dimension, motion on a line. Okay. So okay. Now that we have defined distance, displacement, distance traveled, and we defined position, we have only 1 thing left to be able to discuss kinematics. We need to define time, right? And time is a very fundamental thing that we can only define through the way we measure it. So we can define time, for example, by saying the sun goes up and down after a certain time. So we define that time to be 24 hours, and then we divide it into intervals, and each interval we call hour and so forth. So it's human-made convention. But we can only describe it in terms of change, okay? So we will define the time interval. It's the usual time, we have a clock. So the time interval we will also call it delta t. Again, change in time, because it doesn't really make sense to just define time by itself. If I like when we say 200 BC, what does BC mean? It's before some event, but if I define that 200 BC to be the origin, I can shift the whole timeline, right? So what makes sense to talk about is the change in time, like the difference between 2 events. So this is the T final minus T initial, which is just like T initial now would be 9:42 a.m. and after 2 minutes, it will be 9:44 a.m. So the difference in time will be 2 minutes. Over that time interval, stuff happens and stuff changes. So, so if we have a car starting its motion from traffic light to another traffic light, let's draw that. So let's call that the origin at the first traffic light, and there's the car. And after 1 kilometer, the car is here. So this is the displacement, delta x, the vector displacement. And this change happened during a time interval delta t, the time elapsed. Delta t, let's say it was 30 seconds. Okay, so delta x is 1 kilometer and delta t is 30 seconds. This allows us to define average velocity. So the average velocity is change in position over the time elapsed. So define the average velocity let's call it V with a bar over. Average velocity is defined as delta x over delta t. So the total displacement over the total time elapsed. So in that case, it's 1 kilometer divided by 30 seconds, which is a weird unit. So let's call it. Let's convert that. Actually, we don't have to concern ourselves with conversion. I can just call it covered it in an hour. It's a very slow car. In 1 hour. So the average velocity of that car will be 1 kilometer per hour, which is about half a mile per hour or something. So this is the average velocity. Okay. The average velocity is also a vector quantity, because it has both magnitude and direction. So in this case, the direction of velocity was to the right, so it is a positive quantity. If I have the same thing, but from 1 kilometer to 0, then the velocity would have been negative 1 kilometer per hour, indicating that it's moving to the negative direction. Okay. The reason why we say it's average velocity and not just velocity is because this is not what you read in front of you in the display in your car. Because let's say you were moving in the beginning at 20 miles per hour, and then you accelerated a bit on the highway and got to 50 miles per hour, 60, 70 miles per hour, and then stopped and then moved. So overall, the average velocity that you had from your house to the store will not be accurate description of the velocity along the way, right? It's just an average. The instantaneous velocity, on the other hand, is what you read on the display. And the instantaneous velocity is just the average velocity, but over a very, very, very small amount of time, like infinitesimal amount of time. So let's say 0.0001 seconds, you make that averaging and get a value, and that value is your instantaneous velocity. So instantaneous velocity, velocity is average velocity over an infinitesimal amount of time. And this is what you read on the display. Of course, it's also a vector quantity, and everything of vectors applies to instantaneous velocity. Just as we had displacement and distance, we have velocity and speed. So velocity is a vector quantity that describes both magnitude and direction. It tells you if you're going to the right or to the left. But speed, on the other hand, is just the magnitude or size of velocity. It's a scalar quantity that describes scalar quantity. Let's call it V. Actually, I should have put vector notation on these things above here. So let's make them vectors just to separate them from scalars. Then the speed is just the magnitude of the vector quantity. This is just a notation. It doesn't change anything about the discussion above. And of course, instantaneous speed is just the magnitude of the instantaneous velocity. So all the discussion above carries over. Okay. Okay. So we covered displacement, distance, average velocity, and average speed. So the next item is naturally acceleration, which is the final component in our kinematic equations we will cover next time. But acceleration is the next item. What do you think acceleration will be? Like we had velocity being the change of position over time. What do you think acceleration will be? Right. Change of velocity over time, just like the velocity will change of displacement over time. So acceleration, we denote it as A vector, is the change in velocity over change in time. Okay. And that can be rearranged, like delta V is just V final minus V initial, V final minus V naught over delta T. And with some algebraic manipulation, we can multiply both sides by delta T. So we get V final minus V initial equal A times delta T. And we can put that to the other side. So V final equal V initial plus A times delta T. Guess what? This is the first kinematic equation in this class. So this equation tells us that if we started our motion with some initial velocity and accelerated by some amount over some period of time, our velocity changes and becomes this final velocity. For example, let's say we started from rest. So we were not moving in the beginning. So example, we were not moving. So initial velocity is 0. And let's say you accelerate your car with a rate let's see. 5 meter per second squared. By the way, meter per second squared just means meter per second every second. So it's just velocity change every second. So we write it as meter per second squared. So if the acceleration is 5 meter per second squared, over an amount of time elapsed of, let's say it is half a second. Okay. Then after that half a second, we reach velocity of, we just apply in this formula. So it's 0 plus 5 meter per second squared times half a second. Second cancel with 1 second. So we get 5 over 2 seconds, meter per second, or 2.5 meter per second. So we started from rest and then we reached 2.5 meter per second after half a second. Okay. So this is how you use kinematic equations. Next time we will take one more kinematic equation and we will see some examples on how to apply them to problems and how to calculate acceleration for problems. By the way, I didn't expect to cover all of this today. So actually, instead of just doing problem 1 and 2, you are able to do 3 and 4 with that now. Okay, because 3 and 4 are just average velocity and acceleration. Literally, problem 4 is just calculate the acceleration. You're given the amount of time and you're given the final speed and you're given the initial speed because it starts from rest. It's just a one-line calculation. And problem 3, you are given the average velocity in centimeter per year. And you are asked about the time it takes to reach some distance. Okay, so now you are able to do the first 4 problems. And I would like to stop here because otherwise I will, that will be too fast. So let's just wrap up what we did today. So we defined physics and we motivated why we do physics and we stated some applications of physics. Then we moved on to physics as an experimental science. As an experimental science, we need quantities. So we defined physical quantities. And then we need to measure these physical quantities. So we introduced standardized units so we can agree upon widely all over the world and communicate information. Then we started using kinematics. We started doing kinematics because everything around us in motion. So it's natural to start studying physics, studying motion. We defined our fundamental variables that will help us study motion. Reference frame first, which is this room. An origin of coordinates to refer everything to it. Position, how far an object is from that point. Then displacement, what's the change of the position from point to point. Then time, change in time elapsed over that period. Then everything else follows. Velocity, change in position over change in time. Acceleration, change in velocity over change in time. From that, we arrived at our first kinematic equation. And next time we will derive another kinematic equation and see how we can graph position as a function of time, velocity as a function of time, and acceleration as a function of time on graphs like this one. How to interpret, we will see how to interpret a graph like this. This is a graph of velocity versus time, an idealized graph of the speed of blood. So we will see how to understand these graphs, and we will solve a couple of kinematic equations. I will also give you an activity just to practice please. And on Wednesday, we will see how all of that fit experimentally. We will have some cards and tracks and see how actual physical motion of the cards and your hand, for example, relate to the graphs you see on the computer. Okay. And I think by the end of the week, you will be able to do some problems and then be ready for the quiz. Okay. Any questions or any comments on the pace or anything you want to say, just feel free to. Any questions at all? Really?
I just have a question about the homework.
Question about the homework?
Just a question.
Right. I actually included that in the syllabus. So these are the topics that we will cover. We will cover kinematics, which we started today. Then we will go over forces and Newton's laws, which Chetra will teach you about. Then linear momentum, work and energy, and finally fluids. And fluids, it will be at the end of the month. So we will try to do our best to cover it completely, but I don't promise. But yeah, that's the content, and this is the book. If you just click on the name of the book, it takes you right away to the book online. Okay. What was the other question?
I
How many?
was just wondering
Yeah.
how you access the homework. Is it just under my courses and modules and it'll be
I
posted?
will upload it right after class. I haven't uploaded it yet. I will.
Okay.
I just didn't want to scare you by the homework at the first day, so I wanted to discuss it first. And I will upload it right after class.
All right. Thank you.
Yeah, you're welcome. How many chapters, right? So kinematics is chapter 2 in the book. Let me actually pull up the textbook here. Oh, no. So we're covering kinematics. Okay. All sections of kinematics will be included. We're not covering two-dimensional kinematics, so chapter 3 is skipped. Chapter 4, forces and Newton's laws of motion, we will cover that. We will probably not cover chapter 5, or we can cover a section from it about drag forces. Chapter 6, we will skip entirely. Chapter 7, we will cover most of it. Chapter 8, we will cover most of it. We will skip chapter 9, and we will skip chapter 10. And the final chapter will be a mix of chapter 11 and 12. It will be a very brief, so we will try to cover as much as we can, but you're not expected to cover all of that. Okay. Yeah, that's it for today. If you have any questions, feel free to hang around. Also, I forgot to say that. Please submit your class activity for today. If you have it in paper, just leave it there, and I will collect it. And for people on Zoom, if you worked out the class activity, please email it to me and to Chetra. You will find our emails on the syllabus, okay?
Thank you.
Yeah, you're welcome.